Hello students, Mr. Courtney here. In this video we're talking about chemical composition. We're going to be looking at the relationship between moles and volumes of gases. So our objectives will be to define Avogadro's law, convert volume of a gas at STP, and we'll talk about what STP is also, the number of moles of the gas, and then calculate the molar mass and the density of a gas. Here you would notice that the volumes of 1 mole of different solids are not the same. So what about the volumes of gases? Now, unlike liquids and solids, the volume of moles of gases measured under the same physical conditions are much more predictable. Avogadro proposed an explanation for this, which he stated that equal volumes of gases at the same temperature and pressure have the same number of particles. Now, the particles that make up the different gases, they are not the same size, but the particles in all gases are so far apart that a collection of those relatively large particles do not require much space than the same number of relatively small particles. So you have large space that exists between the individual particles of a gas. So if we look at this, we have 1 mole of helium, 1 mole of oxygen, 1 mole of carbon dioxide. Even though they have different masses, their volumes tend to be the same, and they also have the same number of particles. The volume of a gas changes, or it varies with a change in temperature or a change in pressure. So due to these variations or changes with temperature and pressure, volumes of gases are usually measured at standard temperature and pressure. So the term STP, when we say STP, we mean standard temperature and pressure. The standard temperature is 0 Celsius or 273 Kelvin. Standard pressure, is 101.3 kilopascals or 1 atmosphere. So at STP, 1 mole of a gas contains Avogadro's number of particles, 6.02 times 10 to the 23rd particles. And also at STP, 1 mole of a gas occupies 22.4 liters, or volume of 22.4 liters. That quantity, 22.4 liters, is called the molar volume of a gas. Now, the molar volume is used to convert between number of moles of a gas and the volume of the gas at STP. So this is our molar volume. 1 mole of a gas at standard temperature and pressure occupies 22.4 liters. So we can use either one of these conversion factors to convert from moles of a gas to volume of a gas, or from volume of a gas to moles of a gas. Now, let's add these to the conversion factors we've already learned, or we looked at in terms of the mole. So we already looked at going from mass to mole, or mole to mass, and we know that we use these conversion factors here, and we use the conversion factor that goes in the direction we are headed. So if I'm going from mass to mole, then we're going to use this conversion factor, or from mole to mass, we're going to use this conversion factor. Similarly, we did particles to moles, and again we use this conversion factor to go from moles to particles, and this conversion factor to go from particles to moles. Now, in terms of moles, the volume of the gas at STP. So we're going to start from mole, go to volume of a gas. We use this conversion factor, 22.4 liters over 1 mole. And if we're going from the volume of the gas at STP to moles of the gas, we use 1.00 mole over 22.4 liters. And here, just following this path, we can go from mass to mole to volume, mass to mole to particles, particles to moles to volume. So all these can be connected, and as we see here, they're connected by they have a common connection, and that is the mole. So let's look at some examples. Here we have sulfur. The question says sulfur dioxide is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.60 moles of sulfur dioxide at STP. So here's what we do. Here's what we know. We know how many moles we have. And we know that the relationship, we know the molar volume of a gas is 22.4 liters at STP. So we start with our 0.60 moles, and then we determine which conversion factor we need to use. We put our conversion factor in. Since we're going from moles to volume, we use this conversion factor, 22.4 liters of the gas divided by 1 mole of the gas. Again, our moles of the gas will cancel, which leaves us with 0.60 times 22.4. So essentially, if you're just looking at it mathematically or numerically, you're just multiplying to go from moles of the gas to volume of the gas. You multiply by 22.4 liters. But we have to show our units in terms of our dimensions. And that's the important thing that we need to remember here. We always need to show our units. And that would give us 13 liters of sulfur dioxide. So in this one, at STP, how many moles are in 67.2 liters of sulfur dioxide? So we have the volume and we know the molar relationship. So we're starting with the volume of sulfur dioxide now. That means mathematically we have to divide by the molar volume. Or when we look at it dimensionally, we use the conversion factor of 1 mole of sulfur dioxide over 22.4 liters of sulfur dioxide. Our liters of sulfur dioxide will cancel, which leaves us with moles of sulfur dioxide. And we take 67.2 divided by 22.4, and that gives us 3.00 moles of sulfur dioxide. All right, so now let's look at how molar mass is connected to density. We know that density is the mass per unit volume, and it's measured in grams per liter. And we use grams per liter. And in this case, we use volume of a gas is measured in liters. Molar volume, which is the volume of 1 mole of the gas at standard temperature and pressure, and we know that it's 22.4 liters per mole. All right, so 22.4 liters of gas is in 1 mole of that gas. The molar mass, which is the mass of 1 mole of the compound, or whatever gas it is we have here, would be measured in grams per mole. So how can we use these two, the density and the molar volume, to get our molar mass? So since our molar mass is measured in grams per mole, we can use that relationship to find between density and molar volume and solve that problem dimensionally. So if we take the density and multiply it by the molar volume, grams per liter times liters over 1 mole, or 22.4 liters over 1 mole, our liters will cancel. So here our liters will cancel, and that leaves us with grams per mole, which is the unit of molar mass. So now let's look at 2 examples of using that relationship. So here, the density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP, so standard temperature and pressure. What is the molar mass of the compound? So we look at what we're given. We're given the density. We know the relationship between 1 mole of a gas at STP and its volume is 22.4 liters per mole, and we want to find the molar mass. So we start with our grams per liter, our density, and then we multiply by our conversion factor of 22.4 liters per mole. Our liters will cancel. That leaves us with grams per mole, so 1.964 times 22.4, and that gives us 43.99 grams per mole. So that is the molar mass of the compound. So in this example, we want to find the density of krypton gas at standard temperature and pressure. So to find density, if you remember the equation for density, we need to know the mass and the volume. So density is mass divided by volume. So first thing we need to know is what is the molar mass of krypton. Krypton is an element, so we find its molar mass by looking on the periodic table, and that is the same as its atomic mass. We know the relationship between moles of a gas, between 1 mole of a gas and its volume at STP. That's 22.4 liters per mole. So we already have its molar volume. We want to find the density. So we take the molar mass and we multiply by the conversion factor of 1 mole over 22.4 liters, of 1 mole per 22.4 liters. Our moles will cancel, and that leaves us with 83.8 divided by 22.4 liters. So that gives us in grams per liter, which is a unit of density. And that gives us 3.74 grams per liter. Okay, so we've talked about Avogadro's law. We've looked at the conversion between how we convert from moles of a gas to volume of a gas and volume of a gas to moles of a gas. And we just looked at the relationship between molar volume and molar mass to use that to find the density of a gas, or to find the molar mass of a gas. So that takes us to the end of this video. Until the next time, I'm out. Blessings.